Did you know that dependency injection can simplify how you manage code dependencies? Let's take a look at this example. We have two classes, engine and car. The engine class has a start method to simulate starting the engine. The car class depends on engine. Instead of creating an engine inside the car class, we inject an engine instance through the constructor. This way, when we create a car object and call start, it uses the injected engine instance to start. This approach makes our car class more flexible and easier to test. Let's set up a basic dependency injection container. Here, we create a dependency container class with a method to register dependencies and another to resolve them. By registering dependencies, like engine and car, we store them in a key-value pair. When we need a specific dependency, we simply call the resolve method with the key. This setup allows us to manage dependencies centrally and inject them wherever needed, making our code more modular and easier to maintain. Now, let's inject dependencies into our modules. We have the car service class, requiring a car object. Instead of creating a car instance inside car service, we inject it via the constructor. This is where our dependency container comes in handy. We create a car service instance, injecting the car dependency resolved from our container. When we call start car on car service, it delegates to the car instance's start method. This approach not only simplifies testing but also enhances modularity and code flexibility. Understand the difference between singleton and transient dependencies with this example. We have a logger class, which we want to use as a singleton. This means every time we need a logger, we use the same instance. We register logger in our container as a singleton. Now, look at the notification service, which requires a logger. We inject the singleton logger from our container. When we create an instance of notification service and call send, it uses the same logger instance for logging. This ensures consistency and efficiency in our logging mechanism. Managing dependency lifecycles is crucial. Take the database connection class, for instance. We want a fresh connection for each use, so we register it as a transient dependency in our container. Each time we resolve DB connection, it creates a new instance. Now, let's look at the user repository class, which needs a database connection. By injecting the transient DB connection, every time we create a new user repository, it gets a fresh database connection. This pattern ensures that our database connections are always up to date and isolated for each repository instance. Did you know circular dependencies can be a major pitfall? Look at classes A and B here, each requiring an instance of the other in their constructors. When we try to register these with our container, it creates a circular dependency, which can lead to runtime errors or stack overflow. By catching these errors, we're alerted to the issue. To fix this, we need to refactor our design to remove the circular dependency, ensuring our dependencies are one-way and more manageable. Handling asynchronous code with dependency injection requires special attention. Here we have an async service class with an async method fetch data. Now, consider the client class needing async service. We register async service as usual in our container. When we create a client instance, we inject the async service from the container. Notice how in client's display data method, we await the fetch data method. This setup allows us to handle asynchronous operations smoothly within our dependency injected classes, ensuring that our data loads correctly before we attempt to use it. Let's dive into how dependency injection simplifies testing. Here's a test service class, which logs actions. Normally, it might use a real logger, but for testing, we want to avoid side effects like actual logging. So, we create a mock logger, which just prints a mock log message. We then register this mock logger in our container, replacing the real logger. When we use test service in a test environment, it uses the mock logger, allowing us to test our service's functionality without worrying about the real logging part. This makes unit testing much cleaner and more focused. Exploring advanced techniques, let's talk about lazy injection. Here we have a lazy service class. Instead of creating an instance immediately, we want it to be created only when it's first needed. We achieve this by registering a factory function in our container that checks if lazy service is already instantiated. If not, it creates and stores it. When we resolve lazy service for the first time, the service is instantiated, and subsequent calls use the same instance. This lazy loading approach is efficient, especially for resource-heavy services. Finally, handling errors and exceptions in dependency injection is essential. Take this service class, for example. We're registering and resolving it using our container. However, things might not always go smoothly. Perhaps the service isn't registered correctly, or there's an issue during instantiation. That's why we wrap our resolution logic in a try-catch block. If an error occurs, we catch it and log an error message. This approach ensures our application remains robust and errors in dependency management are handled gracefully, preventing unexpected crashes during runtime.